All right, so this is what it should look like in the beginning, and I'm going to go to here and cross this stuff out. These were just some numbers that somebody else had. So I'm going to ask this group for their numbers and work through here, and then I'll use their numbers to set the spreadsheet up. So what was your number one? What was your starting height? Yeah, from this sheet. I thought you had it together. Is there another group that has it together as well? Oh. Number one, what's the starting height? 0.919? Okay. Okay, and at the end of thrust phase, what was the height? 2.36. Okay, and we don't really need to do this right now. That's when you do your thrust calculations, you're going to need to get this next thing. Delta T during thrust, how long did thrust last? 0.03, so 37 hundredths of a second. And what was the velocity of the rocket after that? Max. 4.37 meters. What for? I was talking. What was the first number? 4.37. And we don't need this. Also, delta V is going to be the same as that. But these are the numbers I need so far. The crash down speed, what'd you get for that? 9.5 meters per second. Yeah, no parachute. The estimated cross-sectional area at the end? 0.1431. It's a very precise estimate. What time did your rocket reach apogee? 3 seconds. What time did the chute begin to, or did it start to break up? We had that as like, so it didn't, so it had the same drag coefficient the whole time, or did it start to? Oh no, we did have some. It was, I think we had it, oh no, it was 7 seconds. 7 seconds? So it got up to the top in 4 seconds. It came down pretty much intact, and after 4 seconds, it. We had something in our sheet, but I don't know anything. You don't have the. 3.7? Okay. And how long did it take it to fully open up, or was that pretty quick? So so if it started opening up, I'll just put 4. Or 3.8 or something. 3.8, because it was pretty quick. Almost instantly broke apart. Right. And they didn't really have a good shoot. It touched the ground. 10 seconds. The dry mass in kilograms? 0.2044. And I don't think we need water volume for this. That's for something else. Cross-sectional area in the very beginning? 0.0143. So it went from, so you're estimating it's got 10 times the cross-sectional area here? I guess. Okay. All right. Yeah, that's fine. And this is not going to be perfect. It's a model. It's the best. I think about the best we can do. But so now I'm just going to put stuff in. The dry mass was 0.2044, and the very first interval launched through separation starts at 0. Coefficient of drag. What do you think in the beginning? Is it kind of an average rocket, better than average rocket, or worse in terms of how aerodynamic it looked when it took off? Okay, I'll just put in 0.3 because that's, I think, for the water rocket simulator online, that's what it's set at. And then chute starts to deploy, or it starts to fall apart at 3.7, and it's fully fallen apart by 3.8. And so what we've got right here is the coefficient of drag is 0.3 at the beginning. And then at 3.7, it's still 0.3. But then it's going to start increasing to, what do you think? I don't know I I asked you to do that yet, but let's come back to that. I'll do 0.143. So if 0.3 is a nice rocket that's flying straight forward, what do you think your rocket might be? 0.5 is a sphere. 0.75 is one of these parachutes, supposedly. 1 is a cube moving sideways through space. What do you think would, just a ballpark guess for coefficient of drag? 0.65. All right, sure. 0.7, because it was a funky thing. All right. So just so you can see here, this is a graph of coefficient of drag versus time. It's I just already set it up. So it stays 0.3, and then it doesn't just instantly jump up to 0.7. It increases over the time interval. So if I scroll down here to 3.7 seconds, you should see at 3.7 seconds, the drag coefficient, yeah, see how it starts to go up to 0.38, then 0.46, and so on and so forth until it's 0.7 there. So I just made it increase linearly, which it probably doesn't, but it's still pretty good for the model. Same thing with cross-sectional area. It's 0.0143, and then it goes up by even steps until it gets to 0.143. All right. So one of the first steps to check this whole thing out might be to, let's look at acceleration versus time. Oh no. Oh yeah, I forgot the yellow parts. Thank you. So this time right over here, this should be 0.037. That's how long thrust lasted. This is right after the thrust is over. The y velocity at the end of that was 44.37. And the y position at the very beginning was 0.919. And the y position at the end of the thrust phase was 2.366. Okay, so now this should look a little more sensible. So this is it. The acceleration is negative in the beginning because it's going up and the net force is down. All it's experiencing is drag going downward and weight going downward. And as drag decreases because it gets slower, that downward net force is less. And eventually, if I keep moving across here, what number am I going to get to soon? See what numbers? I've got negative 10.1, negative 10. Right, somewhere around right there. So at what part of the flight is this? No. End of the thrust is over here. Apogee, yeah. So if you look at the time on here, it's a little less than 3 seconds. If I go to height versus time, the apogee is there. It's at 2.917 seconds, according to the model at the moment. And 2.917 seconds, we've got an acceleration of, I guess it's, yeah, of around negative 9.8. And then it starts to come down. So now we have less downward net force because there's drag pushing up. And then right here, it starts to fall apart and get bigger. So now there's a pretty strong upward drag force, but then it slows down, and here it's approaching zero or terminal velocity. So that's all pretty good. Let's not look at that. I have to fix, for some reason this velocity graph always screws up, and I've got to reset some stuff to get this to work. But this looks pretty good. You would expect a linear slope on this. This is position versus time, and the slope of this is velocity. So here we've got a constant velocity right at the end. All right. So now I'm going to try to align what's here with their actual observed measurements. And the first thing I'm going to do is try to make this match up. So this rocket needs, you can't see what I'm doing. This rocket needs to reach its apogee at 3 seconds. So I'm going to go down the time, and there are a couple ways to do it. One is to keep an eye on the y velocity and see when that reaches the apogee. The other is to go down to 3 seconds. What will the y velocity be at apogee? Highest point. 0. Yeah. So the model right now shows the y velocity going negative at 2.87 seconds, which is really nice. We're almost there. So what I need to do is I need to make my model get to the apogee in a longer period of time, which would suggest that the rocket should go what, lower or higher? Do I need to make this model rocket here go higher or lower? I need to make it go higher. So to make it go higher, what should I do to either the cross-sectional area or the coefficient of drag at the beginning? More drag or less drag? Less. So I could change either one of these. I could change the coefficient of drag to 2.2, I'll try 0.28 and see what that does. Now if I go back to my y velocity and I go down, it looks like it goes negative at 2.937 seconds. So let me do 0.26. I probably overshot. The y velocity goes negative, right at 3 seconds. So good. I mean, right now, at least this is right. So the rocket takes off here and it gets to the top there. But this looks like it's wrong. Their rocket needed to stay in the air for 10 seconds. So I need to adjust the model so it only stays in the air for 10 seconds. So can you think of something I can do so that I don't screw up that first part? So it still reaches the apogee at 3 seconds, but it comes down a little faster? Yeah.
Decrease the coefficient of drag coming down.
So this 0.7, maybe make it 0.6? Okay. Do that, 0.6. So then at 3.8 seconds, instead of having a drag coefficient of 0.6 forever after, it's going to have a drag coefficient of 0.7. And what I'm going to do here is I'm just going to scroll down in y position until y equals what? 0. And then I'm going to look over at the time and see if that's 10 seconds. And if it is, awesome. So now it's 12 seconds. So should I make this drag coefficient bigger or smaller? Even smaller, yeah. So 0.5. Or instead of changing the drag coefficient, what else could I change? Cross-sectional area. So now we're at 11 seconds. So I'm going to drop this cross-sectional area. I'm going to make it 0.1. And I think that might be the better bet because I don't know if right now their rocket was set up so that their cross-sectional area increased by a factor of 10. And I don't know if it would have done that based on what you've told me about your rocket's behavior if it didn't have a parachute. So now that's pretty close. So if I go to height versus time, that would be good enough. But let me just see if I can do a little bit better. I'm going to do 0.95. And it looks like this is maybe the fastest. What I do there? 0.095. I made the parachute huge. Okay. All right. So that looks good. Now the last thing we've been having trouble with this for some reason. This other thing really hasn't been matching up. And the last thing to try to get to match up if you can is the crash down speed, 9.5. So how do I figure out what the crash down speed is here? Yeah, so it's actually in the ballpark. It's negative 8.31. I could mess around with this and try to get that wrangled together. But if at this point you think, oh, it's good enough for our model, you could stay with it. But what could I do to increase this crash down speed? I could decrease either of these. So either I'll decrease this some more. I'll make it 0.9. And thank you, 0.09. So that overdid it. No, it didn't overdo it. It didn't do it enough. 0.08, 0.07. But I'm creating a new problem. What's my new problem? Yeah. So anyway, so now I've got the crash down speed about right, but if I go back to my height versus time, it's not staying in the air long enough. Can anybody think of a way to fix that without screwing up the time to apogee and without screwing up the crashdown speed? What could I do? Just what height? Well, no, the height. Oh, I don't think I can adjust that. I could put in. I'm not going to mess with anything up to here. Something here. I'll just tell you. Here's what I'm thinking. Yeah, I'm going to change the deployment time. So I want this thing to. Oops, sorry. I want it to come down a little bit later. So do I need to get the chute to deploy earlier or later? Earlier. So let's change this to 3.4 and see what that does. And let me change the other one to 3.4. 3. See what that does. It's getting there. Let me move it even earlier. 3.1. And this again, to get this crash down speed right, it seems like you have to take extreme measures with whatever you're doing. That's not really even seeming to have an effect, is it? Let me just do an extreme change. Why isn't it changing at all? Well, if I change the time that it starts, so let me just make sure this is working. So the cross-sectional area at 2 seconds should start to go up, and these other things should start to go up. And it seems like that should, ooh. Oh no, this is all okay. I was looking at the drag and I was thinking, oh, the drag goes from negative to positive, but it really should there. Why should it go from negative to positive? Right. So instead of going up, the thing goes. So I don't know. I feel like this is kind of a lost cause. I'm going to just go back to where I was before and call that good. So when you think you've got the model as closely matched up as you can get it with what you observed, then just call it good. And then so for their acceleration versus time graph, they're going to be printing this out. This is what theirs looks like. So it goes, this is really negative acceleration from all the drag. And here they're getting to the apogee. And then as it starts to fall, they have, it's accelerating downward. And then there's a smaller downward net force because of the effect of its drag coefficient changing. And instead of coming down like this and approaching terminal velocity, theirs is approaching terminal velocity that way. So I think that's all okay. So one of the things they'll be doing when they print this out is making little marks and saying, here's where it's at apogee, this is where the chute deploys, this is right after thrust is over, this is when it's reached terminal velocity. And then I'm going to have you add in a couple of, throw in the impact and the force from thrust over on that side. And force from thrust, you're just going to have an arrow pointing way up. Is this going to be something like, acceleration from thrust is going to be something like 500 meters per second squared that way. So you just draw an arrow and say it should be really positive. So the whole purpose of this was just to show you how you can take the stuff from this sheet and put it in there when you're ready. Some of you aren't ready. Some of you might be done with that. And then once you're done with that, you just follow the instructions on this, which I won't go over.